In this video, I gave you a function and the value of a. What I want you to do is I want you to find the Maclaurin series for the given function using the definition of Maclaurin series and assume that this function has a power series expansion and then also find the associated radius of convergence. So first, this problem works just like the Taylor polynomial. So the only difference is a is always equals to 0. That is a good news because when a is equals to 0, when you plug in a 0 to the derivative, usually the number works out really nice. So for each problem, for the scratch work, or not the scratch work, for the works that you have to show to your instructor, you have to show 3 things. Number 1 is the derivative. Number 2 is you have to plug in the a equals to 0. And then number 3 is you have to find the terms. All right, so let's start with the derivative. So the first one, how many terms do we need? The problem didn't say that, but I prefer to use 5 terms. So when 5 terms, so that will be n equals to 0, 1, 2, 3, and 4. So that is 5 terms. When n is equals to 0, that means we are not taking any derivatives. So this is just 1 minus x raised to the negative 2. And then the first derivative, so this one is you using a power rule. You bring the negative 2 down. And then 1 minus x, negative 2 minus 1 is negative 3. Other than that, do you see that there is a function inside the parenthesis? So we have a linear function inside the x, inside the parenthesis raised to the negative 2. So since there is a function inside another function, we call this a composition function, then you will have to use a chain rule. So chain rule. What is the derivative of 1 minus x? The answer is that is equals to negative 1. This is using chain rule. And then negative 1 times 2 is just a 2. So you have 2 divided by 1 minus x raised to the third. And then the second, when n is equals to 2, double prime, you bring the negative 3 down. But remember, you have negative 1 times 2. So in that case, you have a negative 3 times a positive 2. Then you get a negative 6. And then 1 minus x, negative 3 minus 1 is negative 4. The derivative of the parenthesis, which is 1 minus x, then that produces another negative 1. So this time you have, wait, hold on. 2 times negative 3, negative 6. You have a negative 1 times negative 6, then you have a 6 divided by 1 minus x raised to the 4th, and then n equals to 3. So you bring the negative 4 down, then you have a negative 24. 1 minus x, negative 4 minus 1 is negative 5. And then the derivative of the linear function is negative 1. So you have a 24 divided by 1 minus x raised to the 5th. When n is equals to 4, we have a f of the 4th derivative of x. So this time you bring the 5 down, then you have a negative 120. And then 1 minus x raised to the negative 6. The derivative of the linear function is negative 1. Then you have a 120 divided by 1 minus x raised to the 6. Okay, in a Maclaurin series, we let a equals to 0, right? So a equals to 0, that means you let x equals to 0. Then you have to find f of 0. So let me change that to another color to give you a better comparison. So we have, let's use like a pink, like f of 0. So you have 1 minus 0 raised to the negative 2. So that is just equals to 1. And then first prime at 0, 2 divided by 1 to the third. So that is a 2. Double prime, 6 divided by, let's take a look at how convenient that is. Triple prime, so that is 24 divided by 1 raised to the 5th, which is 24. And then the 4th prime at 0, so that is 120 divided by 1 minus 0 to the 6, which is 1, so you get a 120. But in a Taylor series, if they give you a weird number to plug in, like in this problem, if they let a equals to 2/3, then you have a lot of work to do. So on the test, you hope that you won't get such problem. In my class, I usually make the problem really nice. So if I want to make an exam problem, I will just ask people to do a Maclaurin series because the plugin is easy, and I will just give everybody an easy function. Let's say like f of x equals to e to the x minus 1, something like this. All right, so you got your plugin, and then you have to write your term based on what? Based on this Maclaurin series. So you have a numerator. The numerator is the result of the plugin. Then you have 1 divided by 1 factorial, right? Oh, actually, it's not 1 factorial. The first term is n equals to 0, then that will be 0 factorial. And then you have x minus 0 raised to the 0 power. And then you have a 2 divided by 1 factorial, x minus 0 to the first power. And then a 6 divided by 2 factorial, and then x minus 0, second power, 24 divided by 3 factorial, x minus 0 to the third, and then 120 divided by 4 factorial, and then x minus 0 raised to the fourth. I should use a color to give you a comparison, so this time let me just use a highlighter to divide up the work for you. So that makes everything easy to read. All right, so what is next? The next thing that we will have to do is we have to write the Taylor polynomial, and then we will write the Taylor series. But in this case, since a is equals to 0, we call that a Maclaurin series. All right, so let's do the work in the next piece. So let's return to our orange. So the function f of x is equals to 1 minus x raised to the negative 2. So let's give me the expansion, the Taylor series. So that is equals to, what is the first term equal to? So the first term, this one is equals to 1, right? And then this is equals to 2x. This is equals to 6 divided by 2 is 3. 3x squared. 24 divided by that is 4. And then 120 divided by that is 5. And then what is 4 factorial? 4 factorial is 4 times 3 times 2 times 1. All right, so we have 1 plus 2x plus 3x squared plus 4x to the third, and then plus 5x to the fourth, and then we have to keep going, right? This is only the first 5 terms. We have to keep going because based on the concept of the Taylor/Maclaurin series, the graph of the expansion. So do you see that there is a Taylor polynomial right here? So this is called Taylor polynomial. So the graph of this Taylor polynomial is very similar to the graph of the given function, but you have to use more terms. The more terms you use, the higher similarity you will see. All right, so what about the Taylor series / Maclaurin series? So this one, what is the pattern based on the pink terms we wrote above? So that is, we have to do the summation first. N goes from 0 to infinity, and then what can I do over there? Not the pink terms. Look at the Taylor polynomial above. Don't worry about the pink term. Look at the Taylor polynomial. So can I just do an n? The answer is no. When n is equals to 0, I won't get a 1. So in order to get a 1, this has to be n plus 1, right? And then what about the power? The power is x raised to the nth power, right? So that works. When n is equals to 1, we have the first power. When n is equals to 2, we have a second power. So from the Taylor polynomial to this Maclaurin series, you have to do some lookings. You have to look up and down in order to find this pattern. Don't count on the terms you wrote above. So now I got the Taylor polynomial and the Maclaurin series. The next thing that I would like to do is I would like to determine the radius of convergence. So this, for the radius of convergence, I prefer to use the ratio test. So for the ratio test, I have to compare the nth term and the next term, so the an, which is the entire body of the series, that is n plus 1 times x raised to the n, and then the an plus 1, that is equals to n plus 1, so that will be a plus 2, and then x raised to the n plus 1, and then I want to expand the power a little bit for the simplification purpose, n plus 2, x raised to the n, and then x raised to the first. All right, and then for the ratio test, I will set up a ratio like this. As n approaches to infinity, the absolute value of an plus 1 divided by an, the reason of using absolute value is I want to take away all the alternating terms. But in this Maclaurin series, there is no alternating term, so the absolute value is not going to do anything fancy for you. So as n approaches to infinity, what do we have on top? We have n plus 2 times x to the n, x to the first denominator, n plus 1, and then x to the n. We can do some simplification, x to the n, x to the n, and then the rest. So since n is a 0 or above, we won't get any negative, right? So limit as n approaches to infinity. If you don't want to think too much, you can keep the n inside the absolute value. That won't cause you any points. And then the x, we have to take care of the x because no one said the x is guaranteed past it, right? So the x, we only have one x left, so we put it over there. How come I left some space between the n and the x? Because I have to do something that you learn in differential calculus. How do you evaluate this type of limit? The highest power of the denominator is 1. Do we care the numerator? No, we don't. The highest power of the denominator is 1. I don't care what's in the numerator, don't care at all. So you have to divide each term by 1 divided by n raised to the first power. If the highest degree in the denominator is 5, then that will be 1 divided by n to the 5th. I don't care the numerator. Alright, so back to this problem. So we have n approaches to infinity. Then we have 1 plus 2 divided by n, 1 plus 1 divided by n, so the fraction goes to 0, and then times the absolute value of x, so that is equals to 1 times the absolute value of x, right? So overall, as n approaches to infinity, you have 1 plus 0, 1 plus 0 times x. The absolute value sticks with the x because the x is not guaranteed positive. Then you have the absolute value of x. What else do we have to write? That must be less than 1 to make the series converge. To make the series converge. Why do we have to say this must be less than or equal to 1? Because the given series, we have x raised to the n. We treat that as a geometric series. In order for the geometric series to be convergent, the absolute value of the common ratio, which is not all x in here, must be less than 1 because we treat that as a geometric series. Now, what about the radius of convergence? So still remember that at the video when we talk about radius of convergence, this line stands for x. X is less than 1, that is x between -1 and 1, right? So we have a -1, we have a 1, we use an open circle. How come we don't use a solid circle? Because in order to use a solid circle, you have to let x equals to -1 and then test the convergence or divergence, and then let x equals to -1 to test the convergence or divergence, because this method does not guarantee the convergence on the upper limit and the lower limit of this interval. So this is converge, and then outside of the interval, the series is divergent. So overall, for the radius of convergence, we have to write this -1 less than x less than 1. For the interval notation, you write parentheses -1 and to 1. Usually the problem, they won't ask you to test the two ends because they want to reserve that part for the radius of convergence. So if the section is for radius of convergence to be specific, they will ask you to test. But usually in this type of problem, you have to focus on a Maclaurin or Taylor series. They won't ask you to test the 2n. All right, so that is the end of this video. I will just solve one problem in each video because I don't want to make the tip video too long. What do you think? Did I help you to clear your confusion? If so, let me know in the comment section below. A thank you would be nice. Like the video, subscribe to my channel, share the video for me, let more people visit my channel. I will see you all in the next problem. Signing out for now.